Ahoy CIO class, and welcome to another installment of Chemical Engineering Design. In this lecture, we will take another look at the concept of convection, but in this lecture, we will go into a more insightful detail regarding this. We will be covering the fundamentals once again, which you will be familiar with, but we will also have a look at some of the most important dimensionless numbers that are used in convective heat transfer applications, and also make use of some other analogies to help our understanding, but also to solve certain problems. Think of dimensionless numbers as a way to help us deal with more complex systems in a more simplified manner, where we don't need a lot of parameters. For example, the Mach number is a useful dimensionless number. We know that when the Mach number has reached 1, that we have reached sonic flow. It doesn't matter if that sonic flow is 300 meters per second or 200 meters per second. The Mach number indefinitely tells us that we have reached sonic flow, or that we are over it or under it. And so these dimensionless numbers that will be introduced are very important. Now, convection is all about fluids and the movement of fluids, of course, and how they interact in the presence of temperature gradients and surfaces that are either hotter or colder than the fluids themselves. Our first approach to understanding convection is in the context of flat plates. Why is this the case? Well, because one of the most efficient ways of studying heat transfer, and also heat transfer used today in certain applications, is by sending two fluids, past each other, taking measurements, but also separating them from a flat sheet or conductive surface like a piece of metal. So it's easy to study, but also it's very important in terms of its application. We use it in heat transfer equipment, so we'll come back to these types of heat exchangers a bit later on. So for now, we will at least look at some of the basic understanding of fluids and how they interact with these surfaces. Shown here is a fluid that approaches a flat plate from the left-hand side of the screen. Initially, flow is laminar from the tip of the plate to some distance x critical, where after the flow regime transitions for some distance x until the flow regime is fully turbulent, or rather turbulent flow has been established. In this velocity boundary layer, there are still laminae that are present close to the flat plate surface, very, very close, that remain laminar for all distances of x, and this impacts how heat transfer is accomplished between the fluid and the plate. Remember, the fluid could be the hot entity in this case, and the plate could be cold, or the plate could be hot and it transfers its heat to the fluid instead. Okay, so it doesn't really matter the direction. All that matters is that there is this velocity profile that is being developed across the plate, and also an associated thermal boundary layer, which we'll get into shortly. So recall the term velocity boundary layer from transfer processes. It is defined as a region within the fluid that takes on 99% of the bulk fluid velocity. So shown here is a profile of varying flow rates across a plate, and you can notice that the Reynolds number is changing in accordance, so the Reynolds number gets much higher. This tells us that the velocity is much higher. Notice here that we aren't necessarily talking about the velocity in meters per second. We're actually rather looking at a dimensionless number, the Reynolds number, and looking at how that changes, transitioning from, let's say, 10,000 through to 300,000. So at about 500 1,000 across a plate, you start to get turbulent flow being established. All right, but there's also given here the temperature gradient. So look at how the temperature gradient varies across this velocity boundary layer. This boundary layer, the velocity boundary layer, can be very, very small, and it is defined from where the fluid is stationary on the flat plate until the velocity within the boundary almost reaches the bulk velocity, which is shown here as a capital V as it approaches the flat plate. Okay, we have some we have come across this concept. So we have some knowledge about the no-slip condition before. We dealt with this in transfer processes last semester. And it is often good to illustrate this, obviously, from a picture. A picture, is worth 1,000 words. And so this is some smoke. So it's a smoke-laden fluid, and it runs across a plate on both sides of the plate, so both above and below the plate. Now note that the thick vertical pulse of smoke that has gone across in the inviscid flow region, it's got this very thick pulse, right? It's a very thick vertical pulse. But notice what happens, and compare this with what happens to the way the smoke interacts near the surface of the plate. The smoke smudges itself at the closer part of the part of the fluid that is close to the surface. And this is within the viscous flow regime. And this occurs due to shear stresses. So shear stress becomes an important player in establishing and defining the velocity boundary. Here again we can observe how the laminae of the smoke stream flows across a tennis ball and flows past the tennis ball, and then we have turbulent mixing within the wake of the flow behind the tennis ball. And this is once again caused by the shear stress behind the solid surface as well. It's got to do with inertial forces, etc. Okay. Recall that we previously defined this phenomenon of shear stress using Newton's shear rate equation. At a solid surface, there would be a lot of shear stress, and so we use the following two equations. So here mu is the dynamic viscosity, rho v squared over 2 is the dynamic pressure. Okay, we have dealt with the dynamic pressure before, and then this Cf is a dimensionless friction coefficient. Realize how how increases to the temperature will affect the viscosity of liquids as well as for gases. Look what happens. This might influence frictional losses, for instance, because frictional losses and viscosity are related by the equations as shown. So also notice how the liquid viscosity approaches that of the gases with increases to temperature. So if I increase the temperature of the liquid, I'll tend to have less frictional losses, for example. Note also that the friction coefficient discussed in the heat transfer textbook is exactly the same as the one that we have been using in our piping systems design, this F prime. Okay, so we have frictional pressure drops through pipelines, and we calculate F prime. And so this CF is the same. It is the frictional coefficient. The textbook just uses the notation CF, where the piping systems book just uses the notation F prime. Doesn't the right-hand side of the equation look remarkably similar to the Darcy-Weisbach equation that we have been using for these pressure drops across the pipe sections? almost. Okay, we've got the dynamic pressure shown there, the rho u squared over 2000, and then we've got the frictional losses. Obviously, I've left out the important information, which is the diameter, the hydraulic diameter of the pipe here, and obviously the friction factor in the first equation deals with the surface area for the flat plate. Okay, so these are very, very similar equations. Think about how F prime might be different for pipes versus flat plates. All right, because this is going to be important when we design a plate and frame heat exchanger versus a shell and tube heat exchanger. Now, we've discussed the velocity profile or the velocity boundary layer that forms above and below a flat plate. Let's move on to the thermal boundary layer. Consider how we define density for an ideal gas as the molecular mass m multiplied by P over RT, where the density is therefore inversely proportional to temperature. Therefore, the fluid shown here closest to the hot surface at the bottom would have a slightly lower density than that of the fluid above it. And so what you see here is that the hotter fluid floats upwards and into the surrounding fluid, and in so doing causes a convection that is seen by this motion within the fluid. Okay, so this is how convection looks even for a stationary plate with a stationary fluid above it. Consider again the example that we've used before, where a fluid moves towards a stationary plate as shown and then runs across it. As it approaches the plate, a boundary layer forms from the leading edge to the left-hand side. Okay, so from the leading edge on the left-hand side. The boundary layer is characterized by a velocity gradient towards the plate perpendicular to the bulk fluid motion, the bulk fluid velocity. This velocity boundary layer is also associated with what is termed as the thermal boundary layer due to a temperature gradient. Now, we have defined this before, that this thermal boundary layer is defined in a similar fashion to the velocity boundary layer. So just as the velocity boundary layer begins at a position where the velocity is 99% or less of the bulk velocity, the position of the thermal boundary layer is also defined from the position where the temperature gradient is 99% of that of the bulk velocity temperature gradient, using the stationary plate as the reference point. Since the fluid is not in motion near the surface of the plate, no convection takes place, so heat transfer is via by conduction only. So the conduction that occurs through the fluid layer is given by the Fourier's rate equation as before, using the temperature gradient across this fluid sublayer. And the thermal conductivity, Kf or K fluid, for the fluid, of course. Just above the stationary layer, heat is then transferred by the enhanced motion of the fluid. Okay, so this is the mechanism of convection that we are talking about. Also note that some fluids like water tend to be opaque to radiative heat transfer from the, let's say, from the surface of this flat plate. So therefore only conduction at the surface, close to the surface, and convection through the rest of the fluid would be taking place or would apply. And so something like water, even if the plate is very hot, there won't be radiation as a mechanism. The major mechanisms are convection and conduction. This is obviously not the case when dealing with transparent fluids like that are radiatively transparent, like air, for example. Right. It is difficult to determine the temperature gradient accurately. Okay, you can't just stick thermometers in and disturb the boundary layers. But this can be easily obtained from the properties of the fluid, such as the convective heat transfer coefficient and the thermal conductivity, as well as the temperature gradient between the stationary plate and the bulk fluid. Now, since the temperature gradient Ts minus T bulk is constant throughout, consider what happens to the temperature gradient within the thermal boundary layer. Also think about how this might change when we increase the fluid velocity and therefore its Reynolds number. Okay, Reynolds number is the dimensionless number that we like to consider instead of the velocity, viscosity, etc. Okay, the larger the thermal boundary layer is, the lower the temperature gradient will be, and the smaller the boundary layer is, the larger the temperature gradient will be. So in other words, the convective heat transfer coefficient would decrease as the thermal boundary layer increases, as this would also decrease the heat flux as well. So just keep that in mind. Now let's return to the one example that we have seen before to demonstrate how we can determine the value of H, the convective heat transfer coefficient, all right, and the thickness of the thermal boundary layer using our knowledge of convection and conduction within this boundary layer. We can do this by way of an energy balance. All right, so quickly have a look. You can pause here and see if you can figure out how to solve this problem before moving on. So what we're looking for is H and also the thickness del. So to solve this, we first equate the two equations, since heat transfer in this case would be steady state, and next we substitute in the values, and we can easily calculate the convective heat transfer coefficient to be 750 watt per meter squared Kelvin. The thickness of the thermal boundary layer is computed in a similar way by performing an energy balance. What we do is we make del T, del Y the subject of our equation, and by substituting in our values, we obtain a value for the temperature gradient of minus 25,000 degrees Celsius per meter. Now, can you figure out how to determine the actual thickness from this result? See if you obtain my value of 0.792 millimeter. So, in summary, the thermal boundary layer occurs perpendicular to the solid surface when there is a temperature gradient present between the fluid and the surface. Note that if there is no temperature gradient, that there would be no thermal boundary layer present, even though there may still be a velocity boundary layer present. So this should also be pretty obvious, and therefore we can actually define separate equations. So we can define two equations, one for the velocity boundary layer and one for the thermal boundary layer. Now notice that the thickness del depends on the Reynolds number as well as the distance from the leading edge of the surface, that leading edge of the plate. Okay, so that we're talking about flat plates here. And that in the case of flat plates, we also define a local friction factor, F prime or CFX, or a local friction factor coefficient by the following equation. Okay, so CFX or F prime is equal to 0.664 divided by the square root of the Reynolds number. Okay, now compare this result to the friction factor that we typically will use in piping system design. Okay, so one last thing, the thermal boundary layer is also a function of the Prandtl number. Now, we have not yet defined what the Prandtl number is in this lecture. Now, firstly, the Prandtl number is another dimensionless number, which we typically use in heat transfer applications. It is a property of the fluid, and it is defined by the fluid properties that pertain to the molecular diffusivity of momentum over the molecular diffusivity of heat. So in other words, the Prandtl number is an indication of whether heat is typically transferred predominantly by convection, which is what diffusivity of momentum refers to, or predominantly by conduction, which is what diffusivity of heat is referring to. So for fluids with Prandtl numbers that are larger than 1, convection typically dominates, whereas Prandtl numbers that are less than 1, conduction will be the dominant mechanism of heat transfer. So for example, metals would have much lower Prandtl numbers, while large molecules like those found in heavy oils would have very large Prandtl numbers, exceeding 100,000. Another dimensionless number which we have been discussing throughout the semester and last semester is the Reynolds number, which describes the ratio of the inertial forces as well as the viscous forces of the fluids. And so it's things like the viscosity, the velocity, and also the velocity as it flows through a surface area. So we're talking about the hydraulic diameter, as well as the density, of course, which will also have an effect on the inertia of the fluid. Remember, inertia is a property where the fluid would want to carry on flowing if it is still flowing, or if it is already flowing, it will want to continue to do so, or if it is stationary, it would also want to continue to do so. Okay, so this number describes the presence and persistence of laminae, or broken up pieces of laminae in a fluid as it flows, which is characterized by laminar flow at low Reynolds numbers, as well as turbulent flow at very high Reynolds numbers. Now, the most general equation that we typically use for Reynolds number is defined as follows, okay, and it makes use of the characteristic length in this case, in replace to the hydraulic diameter of flow, which will also be explained shortly. I think we do discuss what we mean by hydraulic diameter. It all depends on the geometry. Is it a flat plate? Is it a square tube? Or is it a round tube like normal piping? So for flat plates, the critical Reynolds number is taken to be 500,000. So this is much higher than what we typically see for piping systems design. Piping systems tend to interact a lot more. The walls of the pipes interact a lot more with the fluid, and that's why the Reynolds numbers for pipes are much lower for this particular transition that we're talking about. The next dimensionless number that we will be dealing with in heat transfer is called the Nusselt's number. It is defined as the ratio of convection or convective heat transfer that is taking place over the conductive heat transfer that is taking place. So what do various numbers, like Nusselt numbers, imply about heat transfer? Well, obviously, Nusselt numbers less than 1, so 0.1, conduction is predominant, and greater than 1, convection is dominant. Okay, so it tells us which heat transfer mechanism is particularly dominant for particular fluid, and obviously we can change this dominance based on the fluid velocity, because the velocity of the fluid affects the convective heat transfer coefficient. Okay, so since the Nusselt number depends on the convective heat transfer coefficient, which is the term that depends on the flow rate, as well as the other properties of the fluid, the Nusselt number is therefore both a function of the Prandtl number, okay, which is talking about momentum transfer and heat transfer, as well as the Reynolds number, which talks about this motion and shear stresses and all of that for the fluid. Okay, now this equation is purely empirical. There's a general form that we will be introduced to shortly. So this particular equation can be used for Prandtl numbers that are larger than 0.6. Such an equation is typically used for things like if you're dealing with a plate and frame heat exchanger. However, the plate and frame heat exchanger also has things like corrugations. So we will require further information to fully define how heat transfer takes place in these sorts of equipment. So which types of equations do you think, not equations, which types of fluids do you think this equation would typically apply? For example, it would apply to air, it would apply to water, but not necessarily to metals like mercury. Okay, so most fluids, you'll be able to use this equation. Some very specialized fluids, you might not. You might need a different form of this equation. Okay. Right, these dimensionless numbers simplify heat transfer problems by reducing the number of parameters required. It does not matter what application we're talking about, these numbers would still apply. So this makes it very easy to make comparisons and computations between various types of heat exchange situations that we might come across. For the case of flat plates, as the boundary layers develop across the plate, the Nusselt number, the Reynolds number, and the Prandtl numbers can be defined, also for inside tubing, etc. And so these dimensionless numbers really reduce the number of parameters considerably, down to 3. Okay. Now, when we look at these dimensionless numbers, we will notice that these numbers are based on position. So we can define a local Nusselt number, we can define a local Reynolds number, but we can also define an average or global Reynolds number and Nusselt number as well. Okay, so keep this in mind. There are equations for these in the textbook that you'll become familiar with once we start doing tutorials in this chapter. Now, it is also possible to non-dimensionalize other dimensions like x and y and the velocities that we are typically going to use in heat transfer. And this is important, as we'll see later when we develop an analogy for heat transfer. Okay, so the following slide that is shown here gives an overall summary of the equations or the parameters that we have already developed. These can also be obtained from the textbook for further reference. Now note that the form of the Reynolds number takes is to the power of n and m, and this is purely empirical and depends on the application. So we can obtain certain values for c, m, and n. Alright, and we'll have a look at this when we look at tubes, flow across tubes and inside tubes as well. We will often use the convective heat transfer coefficient in deciding how well heat is being transferred across certain heat exchange equipment. Now, as we move along with our lessons in heat transfer, we will see more and more how things tie up with piping system design and chemical engineering design. Now, a major portion of chemical engineering design actually has to do with mass transfer and energy transfer. So that's why you've been doing a lot of mass and energy transfer. For mass to be transferred through piping and heat exchange equipment, we will consider the effect that friction has as it relates to the shear stresses and inevitably to the development of the thermal and velocity boundary layers, and also how this affects the heat transfer. So we will consider such properties as the Nusselt number. And here is the crux of it all. The main two things that we are interested in with piping systems, we want to know the friction factor. With heat transfer, we want to know the Nusselt number. And we will end off now with the following. There actually exists a way that we can relate these two phenomena, the one of shear stresses relating to friction factors, and the onset of heat transfer as it relates to the Nusselt number through the fluid. Now, to do this, we consider the following analogy. We relate the momentum and energy for the fluid using the following two equations as the bases. You would have seen these in transfer processes. We're not going to derive them here. Okay, we're just going to discuss them. Notice that there are these two terms in the equations, and that these equations have been non-dimensionalized. and so that both equations are exactly in the same form. And it just so happens that the boundary conditions for the non-dimensionalized velocity and temperature, u star and t star, are also identical, and therefore their functions must also be identical. We can therefore relate the friction factor f prime, or Cfx, to the Nusselt's number by using the following equations introduced previously in this chapter. What is obtained in the end is the Reynolds analogy, which is applicable for Prandtl numbers equal to 1. Now, there are other forms of this equation that may also be used depending on the type of information obtained for a particular problem. However, irrespective of this, the Reynolds analogy is very limited in its application. For example, if we are working with air, we can't use this application, these sets of equations. But fortunately, following from experimental analyses and observations, it was found that the Reynolds analogy may be modified to be applicable to a wider range of fluids as shown here. Now, we will end off this presentation with a quick example. It is also suggested that you as a student go over your textbook. There are lots of examples provided in the textbook, and then you can also attempt some of the tutorials that are applicable to this chapter to help you further understand the context, the content, I mean. In this example, we are told that we are dealing with a flat plate and that air flows along the longer side of the flat plate of 3 meters. Okay, so it's 3 by 2, and the flow is on both surfaces. We are also given the temperature and the velocity of the bulk fluid, along with the drag force that is exerted onto the plate by the flow across both surfaces of the plate. We are then asked to determine the average convective heat transfer coefficient for this plate. This problem does not tell us all the information, but this information the rest of the information that we would need is easily obtained from the reference data that is provided at the back of the textbook, but also online, or any other textbook, even the one for heat transfer, the one for transfer processes will provide you with the same information, or if you're really desperate, you can use Perry's. Obviously, it's a really big reference book, so it's going to take you a while. So for this example, we will use the modified Reynolds number, since the Prandtl number lies within this required range. By using the Nusselt number as well, along with the Reynolds analogy, we can obtain a suitable relation for determining the convective heat transfer coefficient. And what we will now need further is an equation to determine f prime, or Cf. Okay, in this case. For this, we will use the following equation, which is the frictional force, okay, which tells us what the drag force is in terms of the friction factor and the dynamic pressure. Okay, and once we know f prime, we can then calculate the convective heat transfer coefficient. So when I say f prime, I mean this average frictional coefficient. The area here is the total area on which the air blows, so it's on both sides, so times by 2, and therefore the area that we calculate is 12, and we substitute in the rest of the values for the friction coefficient, and we obtain a value of 0.00243. Now, compare this value to the one that we typically get for fluids flowing through pipes of around 0.02, which is 10 times that experienced by this plate. Okay, so you can see the effect that piping has on fluids. The pipe has wrapped itself around the fluid and interacts a lot more, 10 times. Okay. We can now substitute in the values that we have obtained into our equation for the convective heat transfer coefficient, and we're able to calculate a value of 12.7 watt per meter squared Kelvin. And with that, we end off our lecture on the fundamentals of convection.